I've traveled all over the world looking for meteorites, sometimes finding them on the surface, sometimes digging them out from underground. And all the while, in the evenings, I gaze up at the night sky because I've had a lifelong love of astronomy. I'm here at the world-famous Lowell Observatory in Flagstaff, Arizona, where Pluto is discovered, and it's a facility that continues to do cutting-edge astronomical research to this day. And I'm very excited because this journey begins with a meeting with Dr. Simon Porter. He's a brilliant young astronomer who's doing some fascinating work with moons and planets outside of our own solar system.
Author, musician, meteorite hunter, adventurer. I've led an eventful life. Now I'm exploring exciting STEM careers and recording what I find in the STEM journals.
This is spectacular. Simon, I'm looking at the sun through a solar telescope and I'm seeing, I don't know, 10 or 12 sunspots. What's a sunspot?
Sunspot's just a darker area in the sun, and it's darker because it's a little bit cooler, and so it's putting off a little bit less light, and we see it as being dimmer.
And I gather in your work, you spend a lot of time looking not at our sun, but at other stars because you are searching for exoplanets. What's an exoplanet?
An exoplanet's just a planet, but it's a planet that's in a different solar system. Now, most solar systems are not our own, so most planets are exoplanets.
You are searching for alien worlds orbiting distant suns in other solar systems. How does a solar telescope help you with that?
Well, let's go to the telescope and see.
Okay, one more look first. That's just fantastic. I'm playing with a fascinating device here called an orrery. And it's a model of a solar system, a rather small one. It's only got 2 planets. But this very well demonstrates what happened in 2012 during the transit of Venus, when the planet Venus traveled between observers on the Earth, like me, and the sun. How does that relate to your work?
You know, one transit gives you one planet. Multiple transits, you build it up, and you can see that there are multiple planets around the star. You can tell how big the planets are, you can tell how far they are away from the star, so roughly how hot they should be. And if you keep on looking at it for a very long amount of time, you can figure out what their atmospheres are made out of.
Their atmospheres?
Atmospheres.
Okay, I have to think about this for a minute. By using the right kind of equipment, you're able to measure the difference in light from distant stars. That tells you about planets orbiting those stars, and we call them exoplanets. Explain to me how you learn about exomoons.
Exomoons are just moons around exoplanets. And so we try and figure out how these things could exist.
And have you found any yet?
None just yet, but we're on the way.
How will you go about discovering these exomoons, and what can we learn from them?
We detect the exoplanets through looking when they transit in front of the star. If they've got an exomoon going around them, then the exomoon is causing them to move back and forth a little bit, just like the moon causes tides on the Earth. Build up lots and lots of these transits to go back and forth on there, you can start to tell there's something strange there. And that's what an exomoon is.
What tools would help you in your search trying to find exoplanets or exomoons that might possibly support life?
So part of it's the atmosphere. Another big factor is looking at the magnetic field. We know Earth has a nice strong magnetic field that protects us, but magnetospheres are very important for this habitability.
Certainly, but how could you measure a magnetic field from such a great distance?
I think Goligune does exactly that.
When we return to the STEM journals, magnetospheres and high-altitude balloon telescopes.
STEM Journals is sponsored by Copperpoint, proud to sponsor STEM education because students who excel in science, technology, engineering, and math will solve the challenges of tomorrow.
STEM Journal Supplemental. Astronomer Evgenia Shkolnik proposes a brilliant new study to narrow the search for possible habitable exoplanets and answer the question, are we alone in the galaxy?
I'm interested in finding and detecting and characterizing these magnetic fields. Magnetic fields tell us so much about the planet. If we did not have a magnetic field, then the solar radiation, so the high energy protons and electrons that are spewing off the sun and hitting our magnetosphere would actually be hitting our atmosphere and slowly blowing it away.
Ouch.
You don't want that to happen. That was the unfortunate fate, we think, for Mars. It does not have a magnetic field anymore, but we believe that it did once have a magnetic field. And there's plenty of evidence to support that, including the volcanoes that you see behind you. We know that Mars is also rich in volcanoes, which means that in its past it had geologic activity. Potentially in its past it was also habitable.
You study magnetospheres on other planets. You want to find more of them. How could you possibly detect or measure a magnetosphere on an exoplanet that is so very far away from us?
I've been trying to detect magnetic fields on exoplanets for over 10 years. It's really hard. What we've been doing is to look at what the effect that the planet's magnetic field has on its star. And so looking at, say, a hotspot on the star induced by the field as the planet goes around. And coincidentally, just last week, I came back from a big think tank conference going on where we brought together 25 of the world's experts in a variety of fields to brainstorm and to get creative on how to build the technologies we need in order to detect and measure magnetic fields.
How did you become a specialist in studying the magnetospheres of exoplanets?
I did always have an interest in science as a kid, although I never did have a backyard telescope growing up in southern Ontario. Well, I had really no access to astronomy at all, and so I was doing a math and physics undergraduate degree, and around that time is when the first exoplanets were discovered. And that opened up my world completely, and I decided to do a master's and a PhD in astrophysics.
What do you think are the chances of us discovering life on another planet?
Life is probably out there. Almost certainly, given the number of planets in our galaxy alone, it's out there. However, the question is it enough like us that we will be able to identify it?
STEM Journal Supplemental. I had a fantastic time at Lowell Observatory, where the search for exomoons and exoplanets could one day lead to the discovery of life elsewhere in the universe. Now, I'm meeting with Chris Walker and Jenna Kloosterman, who have received a NASA Innovative Advanced Concepts grant to develop a 10-meter suborbital large balloon reflector. I'm pretty sure I've never seen anything like that.
What is this?
It's salsa.
Is that a kind of music? I thought it was hot sauce.
Well, it's also a type of dance and music. Come on, let's try it.
I'm not really much of a dancer.
Come on,
I'm
it'll
more of
be
a
fun.
scientist.
Put your hand on my hip, and your second hand out here, and I'm gonna hold it. My hand goes on your shoulder. And then we're gonna learn the basic, and it's in 7. So you step forward while I step back. 1, 2, 3, 4 is a hold count. 5, 6, 7. Try it one more time.
Okay.
1, 2, 3, 4, 5, 6, 7. Geoff, you're a natural.
Thank you. It's only because I've got such a good teacher. That didn't seem so bad.
Before I was an astronomer, I was a dancer. And actually, I'm a radio astronomer.
What's the difference between conventional astronomy and radio astronomy?
Well, funny you should ask, because most people, when they think of astronomy, they think of the stars they see at night in the sky. And our eyes are evolved here on Earth to observe the light in the optical, because that's where our sun puts out most of its energy. But it turns out that stars and planets and gas clouds and everything else out in space emits light at many, many different frequencies, not just optical light. It does it in the ultraviolet, X-rays, gamma rays, it does it in the infrared, the microwave, and the radio. And our group here at the University of Arizona, we focus a lot on the radio and microwave emission from objects out in space.
Okay, so obviously we all know what a radio is, but how do radio waves factor into your work in astronomy?
Well, just like when you listen on the radio and you wanted to listen to a particular radio station, every radio station has a specific frequency. And likewise, atoms and molecules out in space have specific frequencies that they radiate on. So what our team does is build cosmic radios that can tune into these very high frequencies. You can almost think of these frequencies as being the fingerprint of a particular atom and molecule that we're able to tune in.
So what you're saying then is objects in space, whether it's a sun or a galaxy, they all have their own kind of radio frequency fingerprints. And if you were able to tune into the particular frequency, you could study almost any object that you wanted. What I don't understand is the business with weather balloons. What's the story there?
After the break, we test launch a mock-up of the LBR, and after that, surveying our solar system for Earth-threatening asteroids and comets. STEM Journal, personal log. As a lifelong rock and roller, I never thought I'd hear a scientist use the phrase cosmic radio station. But that's exactly what Chris Walker is doing at the University of Arizona, tuning into the frequencies of space.
This balloon inside, this is going to represent the spherical reflector, and that goes inside this bigger carrier balloon.
I think that's big enough, Jenna.
I'm going to tie this one off now with the second string. Why are we standing on the roof of Stewart Observatory in Tucson with a weather balloon?
We're doing that to demonstrate to you what we're actually going to be flying, hopefully, in a few years with our Large Balloon Reflector project. And in NASA speak, they talk about these type of balloons as high-altitude balloon. A weather balloon is a balloon designed for a specific purpose to measure weather properties. The high-altitude balloons actually go all the way up to about 130,000 feet and can carry payloads that weigh thousands and thousands of pounds.
It seems a little risky to put an expensive telescope inside a fairly primitive transportation device such as this high-altitude balloon model. Why not just send it up in a rocket?
Usually you're limited to about 100 pounds and 100 watts of power for your instrument. With a balloon, we can have a 1,000-pound payload and 1,000 watts of power. The larger the telescope you want to launch, the tinier the piece of the sky is that the telescope looks like, and the more steady your platform needs to be. So our idea was, instead of having our telescope at the end of a long string, why not put the telescope inside the balloon? So we have an outer balloon and an inner balloon, and then the whole outer balloon serves to help stabilize the telescope that we won't so desperately want to put at high altitudes.
Can I say one thing?
Sure.
Ingenious. And away it goes! I was recently at Lowell Observatory, and I was intrigued by the groundbreaking work that they're doing. It makes me curious how you came up with your idea for the balloon research. It's so original.
We launched the balloon from Antarctica, and you could watch it launch, and you could see this huge big balloon above and our little payload hanging underneath. And I kept thinking of how could we make better use of this huge balloon to stabilize our telescope. And then I was coming back from a conference from Bangalore, India last summer. For the next 24 hours on my way back to Tucson, I just made doodles in my lab notebook about how we might be able to realize this idea.
So you're an artist as well. I think the process, the creative process, is very similar in the arts and the sciences. But for truly creative work, I think we need both sides of the brain, the creative and the analytic, to work together.
Couldn't agree with you more.
Well, that's why you come up with the brilliant ideas.
So this right here is our sample receiver unit of something that might go on the balloon. And that signal gets reflected off this particular unit. And this is spray painted with the exact same spray paint that we're going to use on our balloon. So that gets bounced off into the receiver unit. The signal then gets amplified just like your radio. Now, Geoff, you know you're blocking the signal when you do that.
Oh, sorry.
We filter it so we get the specific frequency we're interested in, and it gets amplified again.
Okay, it's very impressive, and it completely reminds me of the lab from Forbidden Planet, which is one of my favorite science fiction films. But what does it actually do?
Well, Geoff, one of the key projects with the Large Balloon Reflector that we want to do is actually to catch the signatures of planets in the process of forming. You know, planets form from the collision of asteroids and comets and things like that. And one of the things that's churned up is water vapor in vast quantities. And by looking for water vapor towards young stars, we can get an idea of how often this planet formation process happens, and also how much water might be present around any particular star. And if we look at this screen, we can actually see these spikes. Just like in the office, we were tuning in frequency, listening to different radio stations. These are different radio signals coming from different atoms or molecules, for instance, like we would see in space. So this one here could correspond to water vapor as we were tuning through.
And I know what that is. That's your favorite cosmic radio station.
Absolutely.
How do all these different aspects of science and technology come together in your work? What's the final result?
Well, what we're trying to do with all this technology, with radios and receivers and telescopes on balloons, in balloons, is trying to open up a new window into our universe, a new way of looking at the formation of stars and planets to better understand how we all got here.
And how ironic is it that all of this work and effort goes into getting the LBR away from the water vapor of Earth so you can find water vapor elsewhere in the universe? Coming up, I'm joined by a young STEM investigator on a mission to find hazardous near-Earth asteroids. STEM Journal, Personal Log. My thoughts keep returning to the LBR and its ingenious and economical solution to a complex problem. How do we move a telescope away from the water vapor of Earth so we can search for water vapor in other solar systems? But now I'm on my way to the Catalina Sky Survey, where I'm excited to meet with Eric Christiansen, who's not only an astronomer, but also a fellow meteorite hunter. And I'm accompanied by one of my best young STEM investigators. Eric, I really hope you've got some kind of amazing cloud filter for your telescopes for tonight.
Well, we don't have a cloud filter, but the clouds occasionally do clear on a moment's notice, so we have to be ready.
What can you tell us about the Catalina Sky Survey?
The Catalina Sky Survey is a program dedicated to the search for near-Earth asteroids that might one day pose a danger to the Earth.
What do you think about that?
That's pretty cool. So when you find an asteroid or a comet, do you get your name on it?
If you find a comet, you do get your name on it. Asteroids have to be named for you.
And I understand you've discovered a couple yourself.
A few, yes.
All right, well, let's step inside, and I'm very keen to see what you have to show us here.
This is our 1.5 meter telescope. This is currently the most productive telescope in the world for near-Earth asteroid discovery. It discovers between 300 and 400 a year, so on average about 1 or 2 a night. In fact, this telescope also discovered 2008 TC3, which was the only near-Earth asteroid discovered before actually impacting the Earth over the Sudan.
Wait, wasn't that the El Mahatasia meteorite?
That's my boy. I trained him myself.
I don't see an eyepiece on this telescope, so how do you discover near-Earth asteroids with this telescope?
Well, that's right, there's no eyepiece. We actually have a camera that's mounted up top at the prime focus, and that's in that configuration in order to get a wide field of view over the sky. In order to discover the near-Earth asteroids, we have to step it through a sequence of images, revisiting the same patch of sky every 10 minutes or so. I can show you more in the control room. It's a little bit easier to see there. So fortunately, it's cleared up. The telescope has finished taking a sequence. What it's done is it's cycled through an area of the sky here near opposition, which is a productive area for near-Earth asteroid searching. It's taken 4 images of each of these pieces of the sky in sequence. And so what it's left with runs through our reduction pipeline. The software extracts the objects from the image, notices which ones are stationary. Anything that's left over is possible moving object candidate. It builds a list, and then we can go through and link these images and visually validate whether or not they're real and whether or not they're interesting.
Are we gonna be like the first people that are seeing this footage, I guess?
That's right. These are hot off the presses, if you will. What do you think this object is?
That definitely looks like something that's moving.
That's a real object. It's not a near-Earth asteroid, though. This is a main belt asteroid. It's not moving very fast, apparently, as viewed from our telescope here on Earth. So that tells us that it's probably pretty far away. In this case, it's out beyond the orbit of Mars.
Whoa.
Whoa! Well, what do you think of this one?
That's going the opposite direction.
Yeah, okay, well, this is definitely a real object, and it's moving the opposite direction, as you pointed out. It's also moving a lot faster. So what we can infer already by that is that it's very close to us, and it's moving in an unusual way. This is definitely a near-Earth asteroid. Now that we've identified this as a potential NEO candidate, we're going to send it off to the Minor Planet Center. And the Minor Planet Center is the clearinghouse of all the asteroid data that we collect. They will post it on a NEO confirmation page. And observers from across the world can have access to this page and see that this object needs confirmation. And actually, some of those people who are doing the confirmation are amateur astronomers.
People that just do this for having fun and have telescopes in their backyard.
Some of them are actually making important contributions. By contributing more data about these objects, we can better understand their orbital characteristics and then use those orbital characteristics to predict any possible danger to the Earth well into the future.
That could be you. STEM Journal, concluding entry. From searching for exomoons and exoplanets at Lowell Observatory to experimenting with radio telescopes at the University of Arizona and detecting asteroids with the Catalina Sky Survey, I've come to realize how innovative astronomers need to be as they try to understand the beginnings and perhaps the end of the universe.
Today I had an absolute blast. I got to discover one of the new near-Earth objects. I'm even more inspired about meteorites, and I need to start asking my teachers and how I can study about this in college and high school, and it's going to be a lot of fun.
Do you have a passion for studying the planets, the stars, the galaxy, and the universe? It all starts in the classroom, and astronomy is a very competitive field. You must make top grades in mathematics and science, especially physics. Join a club at your school. Visit a planetarium. Make sure that you get out there and ask questions to your teachers, to astronomers, and to people that can help you pursue your knowledge in this area.
On the next entry of the STEM Journals, I explore how human beings move and the way our arms, legs, and hands are shaping robotics. That's next week on the STEM Journals.